Embark on a journey to the heart of matter, where the very fabric of reality bends to the will of human ingenuity. Tonight, we delve into the captivating world of plasma physics and fusion energy, exploring how scientists are striving to replicate the power of the stars right here on Earth. Imagine a world powered by clean, sustainable energy, a world free from the constraints of fossil fuels and the looming threat of climate change. This is the promise of fusion, and it all begins with understanding the enigmatic state of matter known as plasma. Plasma, often referred to as the fourth state of matter, is a superheated gas in which electrons have been stripped away from atoms, creating a sea of charged particles. This unique state of matter exhibits extraordinary properties, behaving in ways that are distinct from solids, liquids, and gases. Think of lightning, the aurora borealis, or the solar wind. These are all examples of naturally occurring plasmas, showcasing the immense energy and dynamic behavior inherent in this state of matter. In the context of fusion, plasma serves as the crucible where atomic nuclei are forced to overcome their natural repulsion and fuse together, releasing tremendous amounts of energy in the process. To create and control plasma on Earth, scientists employ sophisticated devices known as tokamaks and stellarators. These machines use powerful magnetic fields to confine and compress the plasma, heating it to temperatures exceeding 100 million degrees Celsius, hotter than the core of the sun. Imagine the challenge of containing something so incredibly hot. It's like trying to hold the sun in your hand, but instead of a hand, we use precisely shaped magnetic fields. The tokamak, with its donut-shaped vacuum chamber, utilizes a combination of magnetic fields to confine the plasma, preventing it from touching the walls of the device and dissipating its energy. The stellarator, a more complex and twisted design, aims to achieve similar confinement, but with greater stability and control. Within these fusion devices, scientists are working to achieve a critical milestone known as ignition, the point at which the energy produced by fusion reactions exceeds the energy required to heat and confine the plasma. Achieving ignition would be a watershed moment, demonstrating the viability of fusion as a practical energy source. It would be akin to achieving sustained flight for the first time, proving that the dream of harnessing the power of the stars is within reach. The pursuit of ignition has driven decades of research and development, pushing the boundaries of science and engineering. The most promising fusion reaction involves the isotopes of hydrogen, deuterium, and tritium. Deuterium is readily available in seawater, while tritium can be produced from lithium, a relatively abundant element. When these isotopes fuse, they form helium and release a neutron, along with a significant amount of energy. This energy can then be harnessed to heat water, create steam, and drive turbines to generate electricity, just like in conventional power plants, but without the harmful greenhouse gas emissions. Think of it as a clean, virtually inexhaustible source of energy powered by the very building blocks of the universe. One of the most ambitious fusion projects in the world is ITER, International Thermonuclear Experimental Reactor, a massive tokamak being built in southern France. ITER is a collaborative effort involving scientists and engineers from around the globe, representing a shared commitment to realizing the potential of fusion energy. The goal of ITER is not to generate electricity commercially, but to demonstrate the scientific and technological feasibility of fusion power. It is a crucial stepping stone towards the development of future fusion power plants that can provide a sustainable and clean energy source for generations to come. The challenges of achieving controlled fusion are immense. Maintaining stable plasma confinement at extreme temperatures is a formidable task. Plasma instabilities like tiny whirlpools and currents can disrupt the confinement and cause the plasma to cool down. Scientists are constantly developing new techniques to control these instabilities, using sophisticated diagnostics and feedback systems. It's like trying to tame a wild beast, requiring patience, skill, and a deep understanding of its behavior. The development of advanced materials that can withstand the extreme heat and radiation within a fusion reactor is another critical area of research. These materials must be able to withstand the constant bombardment of high-energy particles without degrading or becoming radioactive. It's a materials science challenge of the highest order, pushing the limits of what is possible. But the potential rewards of fusion energy are so great that the effort is undoubtedly worthwhile. Fusion offers the prospect of a clean, sustainable, and virtually limitless energy source, reducing our reliance on fossil fuels and mitigating the effects of climate change. Imagine a world where energy is abundant and affordable, where everyone has access to the power they need to thrive. This is the vision that drives the fusion community, inspiring scientists and engineers to overcome the challenges and push the boundaries of human knowledge. The journey towards fusion energy is a long and complex one, but it is a journey that holds the key to a brighter future for all. Let's delve deeper into the heart of these artificial suns, examining the intricate physics that govern their operation. At the core of fusion research lies the understanding of plasma behavior, a realm where classical physics gives way to the complexities of electromagnetism and quantum mechanics. The charged particles within the plasma are constantly interacting with each other and with the magnetic fields that confine them, creating a dynamic and ever-changing environment. Imagine a swirling vortex of charged particles, each particle influenced by the forces of countless others, all orchestrated by the invisible hand of magnetism. This is the essence of plasma confinement, a delicate balance between order and chaos. The magnetic fields used in tokamaks and stellarators are generated by powerful superconducting magnets, cooled to temperatures near absolute zero. These magnets create intense magnetic fields that are thousands of times stronger than the Earth's magnetic field. The precise shaping of these magnetic fields is crucial for achieving stable plasma confinement. Any imperfections or asymmetries in the magnetic field can lead to plasma instabilities and reduced performance. It's like trying to build a perfectly balanced gyroscope. Any slight imbalance can cause it to wobble and fall. One of the key challenges in fusion research is to achieve a high enough plasma density and temperature to sustain fusion reactions. The rate of fusion reactions increases rapidly with temperature, but so does the difficulty of confining the plasma. Scientists are constantly exploring new methods for heating the plasma, including radio frequency waves, microwaves, and neutral beam injection. These techniques are like adding fuel to the fire, raising the temperature of the plasma to the point where fusion can occur. However, it's crucial to add the fuel in a controlled manner, avoiding any sudden bursts or instabilities that could disrupt the confinement. The energy released by fusion reactions is primarily in the form of high-energy neutrons. These neutrons escape the plasma and collide with the walls of the fusion reactor, transferring their energy to the surrounding materials. This energy can then be used to heat water and generate steam, driving turbines to produce electricity. However, the high-energy neutrons can also cause damage to the reactor materials, leading to material degradation and the need for frequent replacement. This is a significant engineering challenge, requiring the development of advanced materials that can withstand the harsh conditions within a fusion reactor. It's like building a shield that can withstand the intense radiation of a nuclear blast, protecting the delicate components inside. The development of fusion energy is not just a scientific and engineering challenge. It is also an economic and political one. Building and operating fusion reactors is a costly undertaking, requiring significant investments in research and development. However, the long-term benefits of fusion energy, including clean, sustainable, and virtually limitless energy, far outweigh the initial costs. It's like investing in a long-term project with the potential to transform the world, creating a better future for generations to come. International collaboration is essential for accelerating the development of fusion energy, sharing knowledge, resources, and expertise. Projects like ITER demonstrate the power of collaboration, bringing together scientists and engineers from around the globe to tackle this grand challenge. Beyond the technical challenges, there are also societal and ethical considerations to address. The deployment of fusion energy will have profound implications for the global energy landscape, potentially disrupting existing industries and creating new opportunities. It's crucial to ensure that the benefits of fusion energy are shared equitably, providing access to clean and affordable energy for all. Public engagement and education are also essential for building support for fusion energy, fostering a better understanding of the technology and its potential benefits. It's like building a bridge between science and society, connecting the researchers and engineers with the people who will ultimately benefit from their work. Let's take a moment to appreciate the sheer audacity of the fusion endeavor. We are attempting to replicate the very processes that power the stars, to harness the energy of the cosmos and bring it down to Earth. It is a testament to human ingenuity and our unwavering pursuit of knowledge. The challenges are formidable, but the potential rewards are immeasurable. The quest for fusion energy is a journey of discovery, pushing the boundaries of science and engineering and inspiring us to reach for the stars. It's a story of collaboration, innovation, and a shared vision for a brighter future. As we continue to unravel the mysteries of plasma physics, and refine our fusion technologies, we move closer to realizing the dream of a world powered by clean, sustainable energy. The future of energy is fusion, and it is a future worth striving for. Consider the historical context of fusion research, tracing its roots back to the early 20th century when scientists first began to unravel the mysteries of the atom. The discovery of nuclear fission in the 1930s led to the development of nuclear weapons and nuclear power, but it also sparked interest in the potential of nuclear fusion. The first attempts to achieve controlled fusion were based on brute force methods, using high-energy beams to collide atomic nuclei. These early experiments were largely unsuccessful, but they laid the groundwork for future research. In the 1950s, scientists began to explore the use of magnetic fields to confine plasma, leading to the development of the tokamak concept. The tokamak, pioneered by Soviet scientists, proved to be a more promising approach, and it quickly became the dominant design for fusion reactors. The decades that followed saw steady progress in fusion research, with gradual improvements in plasma confinement, temperature, and density. However, achieving ignition remained an elusive goal. It was a slow and steady climb, with each step forward building on the knowledge and experience of those who came before. In recent years, there has been a resurgence of interest in fusion energy, driven by growing concerns about climate change and the need for clean energy sources. New technologies, such as high-temperature superconductors and advanced plasma diagnostics, are enabling scientists to push the boundaries of fusion research. Private companies are also entering the fusion arena, bringing new ideas and approaches to the table. The fusion landscape is evolving rapidly, with a diverse range of projects and initiatives underway around the world. It's a dynamic and exciting time for fusion research, with the potential for breakthroughs that could transform the energy landscape. The dream of fusion energy is closer than ever before, and the world is watching with anticipation. Let's explore some of the specific challenges that fusion researchers are grappling with today. One of the most pressing challenges is the development of plasma-facing materials that can withstand the extreme heat and radiation within a fusion reactor. These materials must be able to withstand the constant bombardment of high-energy particles without degrading or becoming radioactive. Researchers are exploring a variety of materials, including tungsten, beryllium, and liquid metals, but finding the ideal material remains a challenge. Another challenge is the control of plasma instabilities, which can disrupt the confinement and cause the plasma to cool down. Scientists are developing sophisticated feedback systems to detect and suppress these instabilities, but achieving stable plasma confinement remains a delicate balancing act. Fueling the plasma with deuterium and tritium is another challenge, requiring the development of efficient and reliable fueling systems. These systems must be able to inject fuel into the plasma without disrupting the confinement. It's a complex engineering puzzle, requiring innovative solutions and precise control. Consider the potential applications of fusion energy beyond electricity generation. Fusion could be used to produce hydrogen, a clean-burning fuel that can be used in fuel cells to power vehicles and other applications. Fusion could also be used to desalinate seawater, providing a source of fresh water for arid regions. The high-energy neutrons produced by fusion reactions could be used to transmute nuclear waste, reducing its radioactivity and making it safer to store. Fusion could even be used to propel spacecraft, enabling faster and more efficient space travel. The possibilities are vast and far-reaching, limited only by our imagination and ingenuity. Fusion is not just an energy source. It is a technology platform with the potential to transform many aspects of our lives. Let's delve into the fascinating world of plasma diagnostics, the tools and techniques that scientists use to probe the inner workings of fusion plasmas. Plasma diagnostics are essential for understanding plasma behavior and optimizing fusion reactor performance. These diagnostics provide information about plasma temperature, density, composition, and magnetic field structure. Scientists use a variety of diagnostic techniques, including spectroscopy, interferometry, and Thomson scattering. Spectroscopy involves analyzing the light emitted by the plasma to determine its composition and temperature. Interferometry uses lasers to measure the density of the plasma. Thomson scattering involves bouncing lasers off the plasma to measure its temperature and density. These diagnostic techniques are like the eyes and ears of the fusion researcher, providing a window into the otherwise invisible world of plasma. The development of advanced plasma diagnostics is crucial for making progress in fusion research. Think about the role of computer simulations in fusion research. Computer simulations are used to model plasma behavior and predict the performance of fusion reactors. These simulations are based on complex mathematical equations that describe the interactions of charged particles and magnetic fields. Scientists use powerful supercomputers to run these simulations, solving millions of equations to simulate the behavior of the plasma. These simulations allow scientists to test different reactor designs and operating scenarios without having to build expensive prototypes. Computer simulations are an essential tool for accelerating the development of fusion energy. They are like a virtual laboratory, allowing scientists to explore the vast parameter space of fusion and identify promising pathways to success. Consider the economic aspects of fusion energy. Fusion reactors are expected to be expensive to build, but they will have low operating costs because the fuel is abundant and inexpensive. The cost of electricity from fusion reactors is expected to be competitive with other sources of electricity, such as fossil fuels and nuclear fission. Fusion energy has the potential to create new jobs and industries, boosting economic growth. The development of fusion energy is an investment in the future, creating a sustainable and prosperous economy for generations to come. It's like planting a seed that will grow into a mighty tree, providing shade and sustenance for all. Reflect on the international collaborations that are driving fusion research forward. ITER is a prime example of international collaboration, bringing together scientists and engineers from around the world to tackle the challenge of fusion energy. Other international collaborations include the Joint European Torus JET in the United Kingdom and the National Spherical Torus Experiment, NSTX, in the United States. These collaborations allow scientists to share knowledge, resources, and expertise, accelerating the development of fusion energy. International collaboration is essential for addressing global challenges, such as climate change and energy security. It's like building a global community, working together to create a better future for all. Let's consider the environmental benefits of fusion energy. Fusion reactors do not produce greenhouse gases, contributing to climate change. Fusion reactors do not produce long-lived radioactive waste, unlike nuclear fission reactors. The fuel for fusion reactors, deuterium and lithium, is abundant and readily available. Fusion energy is a clean, sustainable, and virtually limitless energy source, providing a pathway to a cleaner and healthier planet. It's like cleaning up the air and water, restoring the natural beauty of the Earth. Think about the potential for fusion energy to transform the world. Fusion energy could provide clean, affordable, and reliable energy for all, eliminating energy poverty and boosting economic development. Fusion energy could reduce our reliance on fossil fuels, mitigating climate change and improving air quality. Fusion energy could create new jobs and industries, driving innovation and economic growth. Fusion energy could provide a pathway to a more sustainable and prosperous future for all. It's like building a new world, a world powered by clean energy and driven by innovation. Now, let's delve into the specific challenges that researchers are facing in their quest to achieve sustained fusion. One of the most significant hurdles is maintaining the stability of the plasma. Plasma, being an ionized gas, is inherently unstable and prone to disruptions. These disruptions can cause the plasma to suddenly lose its confinement, leading to a rapid release of energy that can damage the reactor. Scientists are working on developing sophisticated control systems that can detect and mitigate these instabilities in real time. This involves using powerful magnetic fields to confine the plasma and employing feedback mechanisms to adjust the magnetic fields in response to any detected instability. It's a bit like trying to balance a spinning top on your fingertip, constantly making adjustments to keep it from falling over, but on a much grander scale and with far more complex physics involved. Another major challenge is dealing with the heat generated by the fusion reactions. The temperatures inside a fusion reactor can reach hundreds of millions of degrees Celsius, far hotter than the surface of the sun. This extreme heat can damage the materials that make up the reactor. Scientists are developing advanced materials that can withstand these extreme temperatures and resist the erosion caused by the plasma. These materials include tungsten, beryllium, and advanced alloys. They are also exploring innovative cooling techniques, such as using liquid metals to remove heat from the reactor walls. Imagine trying to build a container that can hold the sun. That's the kind of engineering challenge we're talking about. Consider the role of magnetic confinement in harnessing fusion energy. Magnetic confinement is the most common approach to confining the plasma in a fusion reactor. It involves using powerful magnetic fields to trap the charged particles in the plasma and prevent them from escaping. The most widely used magnetic confinement device is the tokamak, a donut-shaped reactor that uses a combination of magnetic fields to confine the plasma. Another promising magnetic confinement device is the stellarator, which uses a more complex magnetic field configuration to achieve better plasma confinement. The challenge is to create a magnetic field that is strong enough and stable enough to confine the plasma for a long enough time to allow fusion reactions to occur. It's like trying to create an invisible cage that can hold a raging fire. A truly remarkable feat of engineering. Think about the alternative approaches to fusion energy, such as inertial confinement fusion. Inertial confinement fusion involves using powerful lasers or particle beams to compress and heat a small target containing deuterium and tritium fuel. The compression creates a high-density plasma that can undergo fusion reactions. The National Ignition Facility in Jeff, in the United States, is the world's largest inertial confinement fusion experiment. While inertial confinement fusion has shown promising results, it still faces significant challenges, such as achieving a high enough energy gain and developing more efficient drivers. It's like trying to create a tiny star in a laboratory, using the power of lasers to compress matter to unimaginable densities. Let's explore the historical context of fusion research. The quest for fusion energy began in the 1950s, with early experiments showing promising results. However, it soon became clear that achieving sustained fusion was a much more difficult challenge than initially anticipated. Over the decades, scientists have made significant progress in understanding plasma physics and developing the technologies needed to build fusion reactors. The ITER project is a testament to the international commitment to fusion research, bringing together scientists and engineers from around the world to build the world's largest tokamak. The history of fusion research is a story of perseverance, innovation, and international collaboration, driven by the dream of a clean and sustainable energy future. It's a journey that has taken us from simple experiments to complex machines, all in the pursuit of harnessing the power of the stars. Reflect on the connections between fusion energy and other areas of science and technology. Fusion research has led to advances in plasma physics, materials science, and computer modeling. The technologies developed for fusion reactors have applications in other fields, such as medicine, manufacturing, and space exploration. Plasma technologies are used in medical devices, such as sterilizers and surgical instruments. Advanced materials developed for fusion reactors are used in aerospace and other industries. Computer modeling techniques developed for fusion simulations are used in a wide range of scientific and engineering applications. Fusion energy is not just about creating a new energy source. It's about advancing science and technology across the board. It's like a catalyst that spurs innovation in many different fields. Consider the economic implications of fusion energy. Fusion energy has the potential to transform the global energy landscape, creating new jobs and industries. The development of fusion reactors will require significant investment, but the long-term benefits are enormous. Fusion energy could provide a clean, sustainable, and virtually limitless energy source, reducing our reliance on fossil fuels and mitigating climate change. The cost of electricity from fusion reactors is expected to be competitive with other sources of electricity, such as fossil fuels and nuclear fission. Fusion energy is an investment in the future, creating a sustainable and prosperous economy for generations to come. It's like investing in a technology that will pay dividends for centuries to come. Now, let's think about the ethical considerations of fusion energy. Fusion energy is a clean and sustainable energy source, but it also raises ethical questions. Who will have access to fusion energy? How will fusion energy be used? How will the environmental impacts of fusion reactors be minimized? These are important questions that need to be addressed as fusion energy becomes a reality. It's important to ensure that fusion energy is used for the benefit of all and that its environmental impacts are minimized. It's like having a powerful tool that can be used for good or for ill. It's our responsibility to ensure that it's used wisely. Let's delve deeper into the specific materials challenges in fusion reactors. The materials used in fusion reactors must be able to withstand extreme temperatures, high radiation levels, and corrosive environments. Tungsten is a leading candidate for the divertor, a component that removes heat and impurities from the plasma. Beryllium is used in the first wall, which protects the reactor from the plasma. Advanced alloys, such as reduced activation ferritic martensitic steels, are being developed for the structural components of the reactor. The challenge is to develop materials that can maintain their structural integrity and performance under these extreme conditions for long periods of time. It's like trying to build a shield that can withstand the full force of a star. Consider the role of computer simulations in fusion research. Computer simulations are essential for designing and optimizing fusion reactors. They allow scientists to model the behavior of the plasma, predict the performance of different reactor designs, and test different operating scenarios. These simulations require enormous computational resources, often using supercomputers to solve complex equations. The accuracy of the simulations depends on the quality of the models and the availability of experimental data. Computer simulations are an indispensable tool for accelerating the development of fusion energy. It's like having a virtual laboratory where scientists can explore the vast parameter space of fusion and identify promising pathways to success. Think about the different types of fusion reactions that are being explored. The most common fusion reaction involves deuterium and tritium, two isotopes of hydrogen. However, other fusion reactions are also being investigated, such as deuterium-deuterium and deuterium, helium-3. These reactions have different energy yields and require different plasma conditions. The choice of fusion reaction depends on the specific reactor design and the desired performance characteristics. It's like choosing the right fuel for a rocket. It depends on the mission and the capabilities of the rocket. Reflect on the role of international collaboration in fusion research. Fusion energy is a global challenge that requires international collaboration. The ITER project is a prime example of international collaboration, bringing together scientists and engineers from around the world to build the world's largest tokamak. Other international collaborations include the Joint European Torus, JET, in the United Kingdom and a National Spherical Torus Experiment, NSDX, in the United States. These collaborations allow scientists to share knowledge, resources, and expertise, accelerating the development of fusion energy. International collaboration is essential for addressing global challenges, such as climate change and energy security. It's like building a global community, working together to create a better future for all. Let's consider the environmental benefits of fusion energy in more detail. Fusion reactors do not produce greenhouse gases, contributing to climate change. Fusion reactors do not produce long-lived radioactive waste, unlike nuclear fission reactors. The fuel for fusion reactors, deuterium and lithium, is abundant and readily available. Fusion energy is a clean, sustainable, and virtually limitless energy source, providing a pathway to a cleaner and healthier planet. It's like cleaning up the air and water, restoring the natural beauty of the Earth. The only radioactive waste produced is the reactor itself, which can be recycled or disposed of after a relatively short period. This is a significant advantage over nuclear fission, which produces waste that remains radioactive for thousands of years. Think about the potential for fusion energy to transform the world. Fusion energy could provide clean, affordable, and reliable energy for all, eliminating energy poverty and boosting economic development. Fusion energy could reduce our reliance on fossil fuels, mitigating climate change and improving air quality. Fusion energy could create new jobs and industries, driving innovation and economic growth. Fusion energy could provide a pathway to a more sustainable and prosperous future for all. It's like building a new world, a world powered by clean energy and driven by innovation. Imagine a world where energy is so abundant and cheap that it is essentially free, a world where everyone has access to the power they need to thrive. Now, let's explore the challenges of achieving ignition in a fusion reactor. Ignition is the point at which the fusion reactions generate enough heat to sustain themselves, without the need for external heating. Achieving ignition is a major milestone in fusion research, as it demonstrates that the reactor can produce more energy than it consumes. The ITER project is designed to achieve ignition, paving the way for commercial fusion power plants. The challenge is to create a plasma that is hot enough, dense enough, and confined long enough to achieve ignition. It's like lighting a fire. You need to get the conditions just right for the fire to catch and sustain itself. Consider the different types of magnetic confinement devices. The tokamak is the most widely used magnetic confinement device, but other devices are also being explored, such as the stellarator and the spherical tokamak. The stellarator uses a more complex magnetic field configuration to achieve better plasma confinement, while the spherical tokamak is a more compact and efficient design. Each type of device has its own advantages and disadvantages, and the choice of device depends on the specific research goals. It's like choosing the right tool for the job. Each tool has its own strengths and weaknesses. Let's delve into the physics of plasma confinement. Plasma is a state of matter in which atoms are ionized, meaning that they have lost or gained electrons. This creates a gas of charged particles that can be confined by magnetic fields. The magnetic field exerts a force on the charged particles, causing them to spiral around the magnetic field lines. This prevents the particles from escaping the plasma, confining them within the reactor. The strength and configuration of the magnetic field are crucial for achieving good plasma confinement. It's like creating an invisible bottle that can hold a superheated gas. Think about the role of turbulence in plasma confinement. Turbulence is a chaotic motion of the plasma that can lead to heat loss and reduced confinement. Understanding and controlling turbulence is a major challenge in fusion research. Scientists are developing sophisticated computer models to simulate the behavior of turbulence and identify ways to mitigate its effects. They are also exploring innovative techniques, such as using electric fields to suppress turbulence. It's like trying to calm a stormy sea. You need to understand the forces that are driving the turbulence and find ways to dampen them. Reflect on the potential applications of fusion energy beyond electricity generation. Fusion energy could be used to produce hydrogen, desalinate water, and treat nuclear waste. Hydrogen is a clean-burning fuel that can be used in transportation and other applications. Desalination can provide fresh water in arid regions. Fusion reactors could be used to transmute long-lived radioactive waste into shorter-lived isotopes, reducing the burden of nuclear waste disposal. Fusion energy is not just about generating electricity. It's about solving some of the world's most pressing challenges. It's like having a versatile tool that can be used for a variety of purposes. Let's consider the challenges of building and operating a fusion reactor. Fusion reactors are complex and expensive machines that require advanced engineering and technology. The construction of ITER, for example, is estimated to cost billions of dollars. The operation of a fusion reactor requires highly skilled personnel and sophisticated control systems. The challenge is to develop cost-effective and reliable fusion reactors that can be operated safely and efficiently. It's like building a spaceship. It requires a massive investment of resources and expertise. Think about the role of public support in fusion research. Fusion research is a long-term endeavor that requires sustained public support. Public support is essential for securing funding for research and development, and for creating a favorable regulatory environment for fusion energy. It's important to educate the public about the benefits of fusion energy and to address any concerns they may have. Public support is crucial for realizing the potential of fusion energy. It's like building a bridge. It requires the support of the community to make it a reality. Now, let's explore the future of fusion energy. Fusion energy is still in the research and development phase, but significant progress has been made in recent years. The ITER project is expected to demonstrate the feasibility of fusion energy, paving the way for commercial fusion power plants. It is likely that fusion energy will play an increasingly important role in the global energy mix in the coming decades. Fusion energy has the potential to provide a clean, sustainable, and virtually limitless energy source for generations to come. It's like looking into the future and seeing a world powered by clean energy. Consider the potential for fusion energy to address climate change. Climate change is one of the most pressing challenges facing humanity, and fusion energy could play a crucial role in mitigating its effects. Fusion reactors do not produce greenhouse gases, contributing to climate change. By reducing our reliance on fossil fuels, fusion energy can help to reduce greenhouse gas emissions and slow down the rate of climate change. Fusion energy is a key part of the solution to climate change. It's like having a powerful weapon in the fight against climate change. Let's delve into the specific challenges of maintaining plasma purity. Impurities in the plasma, such as heavy elements, can radiate away energy and reduce the efficiency of fusion reactions. Maintaining plasma purity is therefore essential for achieving high performance in a fusion reactor. Scientists are developing techniques to remove impurities from the plasma, such as diverters and impurity injection. The challenge is to develop effective and reliable methods for maintaining plasma purity. It's like keeping a clean room. You need to prevent any contaminants from entering. Think about the role of diagnostics in fusion research. Diagnostics are instruments that are used to measure the properties of the plasma, such as temperature, density, and magnetic field. These measurements are essential for understanding the behavior of the plasma and for optimizing the performance of the reactor. Scientists are developing advanced diagnostic techniques to probe the plasma with greater precision and accuracy. It's like having a set of sensors that can tell you everything that is happening inside the reactor. Reflect on the potential for fusion energy to create new jobs and industries. The development of fusion energy will require a skilled workforce in a variety of fields, such as engineering, physics, and materials science. The construction and operation of fusion reactors will create new jobs in manufacturing, construction, and energy production. Fusion energy has the potential to stimulate economic growth and create new opportunities for workers. It's like creating a new industry from scratch, with all the associated jobs and economic benefits. Let's consider the challenges of licensing and regulating fusion power plants. As fusion energy becomes a reality, it will be necessary to develop a regulatory framework for licensing and operating fusion power plants. This framework will need to address issues such as safety, environmental protection, and waste management. The challenge is to create a regulatory framework that is both effective and efficient, allowing fusion energy to be deployed safely and responsibly. It's like creating a set of rules for a new game. You need to ensure that the game is fair and safe for everyone. Think about the role of education and outreach in fusion research. Education and outreach are essential for building public support for fusion research and for attracting talented young people to the field. It's important to educate the public about the benefits of fusion energy and to inspire the next generation of scientists and engineers. Education and outreach are crucial for realizing the potential of fusion energy. It's like planting seeds that will grow into a forest of knowledge and innovation. Now, let's explore the potential for fusion-fission hybrid reactors. Fusion-fission hybrid reactors combine the benefits of both fusion and fission technologies. Fusion reactions are used to produce neutrons, which are then used to breed fuel for fission reactors. This can enhance the efficiency of fission reactors and reduce the amount of nuclear waste they produce. Fusion-fission hybrid reactors could play a role in the transition to a sustainable energy future. It's like combining two different technologies to create a more powerful and versatile system. Consider the challenges of developing and deploying fusion energy in developing countries. Developing countries often face unique challenges in accessing clean and affordable energy. Fusion energy could provide a solution to these challenges, but it will be necessary to develop technologies that are appropriate for the specific needs of developing countries. This may involve developing smaller, more modular fusion reactors that can be deployed in remote areas. It's like tailoring a technology to meet the specific needs of a particular community. Let's delve into the specific challenges of achieving high energy gain in inertial confinement fusion. Energy gain is the ratio of the energy produced by fusion reactions to the energy used to compress and heat the fuel. Achieving high energy gain is essential for making inertial confinement fusion a viable energy source. The National Ignition Facility, NGEF, is working to achieve high energy gain by improving the efficiency of the lasers and by optimizing the design of the fuel targets. It's like trying to squeeze as much energy as possible out of a tiny package. Think about the role of advanced materials in fusion energy. Advanced materials are essential for withstanding the extreme conditions inside a fusion reactor. These materials must be able to withstand high temperatures, high radiation levels, and corrosive environments. Scientists are developing new materials, such as advanced alloys and ceramics, that can meet these demanding requirements. It's like building a suit of armor that can protect you from the harshest environments. Reflect on the potential for fusion energy to address water scarcity. Water scarcity is a growing problem in many parts of the world. Fusion energy could be used to power desalination plants, which can convert seawater into fresh water. This could provide a sustainable source of fresh water for communities that are facing water shortages. Fusion energy is not just about generating electricity. It's about solving some of the world's most pressing challenges. It's like having a tool that can turn seawater into drinking water. Let's consider the challenges of managing the tritium fuel cycle in fusion reactors. Tritium is a radioactive isotope of hydrogen that is used as fuel in fusion reactors. Tritium is relatively rare and expensive, so it is important to manage the tritium fuel cycle carefully. This involves breeding tritium from lithium inside the reactor and recycling the tritium that is not consumed in fusion reactions. The challenge is to develop efficient and safe methods for managing the tritium fuel cycle. It's like carefully managing a precious resource to ensure that it is not wasted. Think about the role of artificial intelligence, AI, in fusion research. AI can be used to analyze large data sets, control complex systems, and optimize reactor performance. AI algorithms can be used to predict plasma instabilities, control the magnetic fields, and optimize the fuel injection. AI has the potential to accelerate the development of fusion energy and to improve the performance of fusion reactors. It's like having a smart assistant that can help you to run the reactor more efficiently. Now, let's explore the potential for fusion energy to power space exploration. Fusion energy could provide a powerful and efficient source of power for spacecraft, enabling them to travel faster and farther. Fusion reactors could be used to power electric propulsion systems, which can provide a continuous thrust for long-duration missions. Fusion energy could also be used to provide power for habitats on other planets. It's like having a powerful engine that can take us to the stars. Consider the challenges of developing and deploying fusion energy in a competitive energy market. Fusion energy will need to be cost competitive with other sources of energy, such as fossil fuels and renewable energy. This will require reducing the cost of building and operating fusion reactors and improving their performance. The challenge is to make fusion energy an attractive investment for utilities and other energy providers. It's like launching a new product into a crowded marketplace. You need to make it better and cheaper than the competition. Let's delve into the specific challenges of achieving stable plasma confinement in stellarators. Stellarators use a complex magnetic field configuration to achieve better plasma confinement than tokamaks. However, designing and building stellarators is a challenging task, and it is difficult to ensure that the plasma is stable and well confined. Scientists are working to optimize the design of stellarators and to develop control systems that can stabilize the plasma. It's like trying to balance a complex mobile. You need to get the weight distribution just right to keep it from falling over. Think about the role of advanced manufacturing techniques in fusion energy. Advanced manufacturing techniques, such as 3D printing, could be used to fabricate complex components for fusion reactors. This could reduce the cost and lead time for building fusion reactors and enable the creation of new and innovative designs. Advanced manufacturing has the potential to revolutionize the way fusion reactors are built. It's like having a machine that can create almost anything you can imagine. Reflect on the potential for fusion energy to contribute to a more peaceful and equitable world. Energy security is essential for economic development and political stability. Fusion energy could provide a clean, sustainable, and virtually limitless energy source for all countries, reducing the risk of conflict over energy resources. Fusion energy has the potential to contribute to a more peaceful and equitable world. It's like providing everyone with the resources they need to thrive, reducing the potential for conflict and inequality. Let's consider the challenges of ensuring the safety and security of fusion reactors. Fusion reactors do not produce long-lived radioactive waste, but they do use tritium, a radioactive isotope of hydrogen. It is important to ensure that tritium is handled safely and securely to prevent any accidental releases. Fusion reactors also need to be protected from sabotage and terrorism. The challenge is to develop robust safety and security measures that can protect the public and the environment. It's like building a fortress that can withstand any threat. Think about the role of international cooperation in addressing the challenges of fusion energy. Fusion energy is a global challenge that requires international cooperation. Scientists and engineers from around the world need to work together to share knowledge, resources, and expertise. International cooperation is essential for accelerating the development of fusion energy and for ensuring that it is used for the benefit of all. It's like building a global team that is working toward a common goal. Now, let's explore the potential for fusion energy to inspire future generations of scientists and engineers. Fusion energy is a grand challenge that can inspire young people to pursue careers in science, technology, engineering, and mathematics STEM. By showcasing the exciting possibilities of fusion energy, we can attract talented young people to the field and ensure that we have the workforce we need to develop and deploy this important technology. It's like lighting a spark that can ignite a lifelong passion for science and engineering. Consider the challenges of translating fusion research from the laboratory to the marketplace. Many promising fusion technologies have been developed in the laboratory, but it can be difficult to translate these technologies into commercial products. This requires overcoming technical challenges, securing funding, and navigating the regulatory landscape. The challenge is to create an ecosystem that supports the commercialization of fusion technologies. It's like building a bridge between the laboratory and the marketplace. Let's delve into the specific challenges of achieving long pulse operation in fusion reactors. Long pulse operation is essential for demonstrating the viability of fusion energy. This requires maintaining stable plasma conditions for extended periods of time, which can be challenging due to plasma instabilities and material limitations. Scientists are working to develop control systems and materials that can enable long pulse operation. It's like running a marathon. You need to pace yourself and maintain your stamina to reach the finish line. Think about the role of data science in fusion research. Fusion experiments generate vast amounts of data, which can be used to improve our understanding of plasma physics and to optimize reactor performance. Data science techniques, such as machine learning and data mining, can be used to analyze these data and to extract valuable insights. Data science has the potential to accelerate the pace of fusion research. It's like having a powerful microscope that can reveal hidden patterns in the data. Reflect on the potential for fusion energy to empower communities and promote social justice. Access to clean and affordable energy is essential for economic development and social well-being. Fusion energy could provide a sustainable energy source for communities that are currently underserved, empowering them to improve their lives and to participate more fully in society. Fusion energy has the potential to contribute to a more just and equitable world. It's like providing everyone with the tools they need to build a better future. Let's consider the challenges of engaging the public in discussions about fusion energy. It is important to engage the public in discussions about the benefits and risks of fusion energy and to address any concerns they may have. This requires communicating complex scientific information in a clear and accessible way and listening to the perspectives of different stakeholders. The challenge is to create a dialogue that is informed, respectful, and productive. It's like having a conversation with your neighbors about a new project in your community. Think about the role of creativity and innovation in fusion research. Fusion research is a challenging and complex endeavor that requires creativity and innovation. Scientists and engineers need to think outside the box and to develop new and innovative solutions to the challenges they face. Creativity and innovation are essential for realizing the potential of fusion energy. It's like having a blank canvas and the freedom to create something new and amazing. Now, let's explore the potential for fusion energy to contribute to a more sustainable and resilient future. Fusion energy is a clean, sustainable, and virtually limitless energy source that can help us to build a more sustainable and resilient future for all. By reducing our reliance on fossil fuels, mitigating climate change, and providing access to clean and affordable energy, fusion energy can help us to create a world that is more prosperous, equitable, and environmentally sound. It's like building a house that is strong, sustainable, and beautiful. The journey towards harnessing star power on Earth is a long and arduous one, filled with complex scientific and engineering challenges. But the potential rewards are so great. A clean, sustainable, and virtually limitless energy source that the effort is undoubtedly worthwhile. As we continue to push the boundaries of science and technology, we move ever closer to realizing the dream of fusion energy, a dream that promises to transform our world and secure a brighter future for generations to come. So, let us continue to explore, to innovate, and to collaborate until we finally unlock the power of the stars and bring it down to Earth. And as you drift off to sleep tonight, remember that somewhere in the world, scientists and engineers are working tirelessly to make this dream a reality, a dream that could one day power our homes, our cities, and our future. Sweet dreams, and may the power of the stars be with you. But the quest for fusion energy doesn't end with the scientific breakthroughs and engineering marvels. It extends into the realm of material science, where researchers are constantly seeking new materials that can withstand the extreme conditions within a fusion reactor. Imagine the relentless bombardment of neutrons, the intense heat, and the powerful magnetic fields, all conspiring to degrade and weaken the very materials that contain this miniature sun. It's like trying to build a fortress that can withstand the fury of a star, a task that requires ingenuity, precision, and a deep understanding of the properties of matter. Scientists are exploring advanced alloys, ceramics, and composite materials, pushing the boundaries of what's possible to create a reactor vessel that can endure the harsh realities of fusion. Think of the challenges faced by medieval alchemists trying to transmute base metals into gold. But instead of gold, the goal is a substance that can contain the power of a star. And speaking of challenges, let's delve a little deeper into the intricacies of plasma confinement. Creating a plasma is one thing, but keeping it stable and confined long enough for fusion to occur is an entirely different ballgame. The plasma, a superheated soup of charged particles, has a natural tendency to escape its magnetic cage, leading to energy loss and ultimately hindering the fusion process. It's like trying to hold water in your hands. It slips through your fingers no matter how tightly you clench them. Scientists use complex magnetic field configurations to create what they call magnetic bottles, designed to trap the plasma and prevent it from touching the walls of the reactor. The shape and strength of these magnetic fields must be precisely controlled to maintain plasma stability and maximize fusion reactions. The slightest disturbance can lead to disruptions, causing the plasma to quench and the fusion process to cease. Imagine a delicate dance where the plasma must be guided and coaxed into staying within its boundaries. A dance that requires a deep understanding of plasma physics and sophisticated control systems. Consider also the challenges of fuel production. While the deuterium used in many fusion experiments is readily available from seawater, the tritium is much rarer and more difficult to obtain. Tritium is radioactive, and its natural abundance is very low, making it necessary to produce it artificially. One promising approach is to breed tritium within the fusion reactor itself, using neutrons produced during fusion reactions to bombard lithium, a common element found in the Earth's crust. This process, known as tritium breeding, would create a self-sustaining fuel cycle, ensuring a continuous supply of tritium for fusion reactors. It's like planting a garden that not only provides food, but also replenishes its own soil, creating a sustainable ecosystem. Scientists are actively researching and developing tritium breeding technologies to ensure a reliable and sustainable fuel supply for future fusion power plants. Think of the ingenuity of early farmers who learned to cultivate crops and manage resources to ensure a consistent food supply for their communities. Now, let's turn our attention to the international collaboration that is driving fusion research forward. Fusion is a global endeavor, with scientists and engineers from around the world working together to overcome the challenges and unlock the potential of this transformative energy source. The International Thermonuclear Experimental Reactor, ITER, a massive fusion experiment being built in France, is a prime example of this international collaboration. ITER brings together researchers from Europe, the United States, Russia, China, Japan, South Korea, and India, pooling their expertise and resources to build the world's largest tokamak, a type of fusion reactor that uses powerful magnetic fields to confine plasma. It's like building a cathedral, a project that requires the collective effort of many skilled artisans and builders, each contributing their unique talents to create something truly magnificent. ITER is a testament to the power of international cooperation and the shared commitment to solving one of the world's most pressing challenges, the need for clean and sustainable energy. But the path to fusion energy is not without its critics. Some argue that fusion is too expensive, too complex, and too far off in the future to be a viable solution to our energy needs. They point to the decades of research and development that have already been invested in fusion, with no commercial fusion power plants yet in operation. Others raise concerns about the safety and environmental impacts of fusion, particularly the handling of tritium and the potential for accidents. These are valid concerns that must be addressed through rigorous research, careful planning, and transparent communication. It's like building a bridge. You need to carefully consider the costs, the risks, and the benefits before embarking on such a complex undertaking. Scientists and engineers are working hard to address these concerns and to demonstrate the safety and viability of fusion energy. Think about the economic implications of fusion energy. If fusion energy becomes a reality, it could have a profound impact on the global economy. A virtually limitless supply of clean energy could drive economic growth, create new industries, and reduce our dependence on fossil fuels. Fusion power plants could be built anywhere in the world, providing energy independence and reducing the geopolitical tensions associated with fossil fuel resources. It's like discovering a new continent rich in resources, a discovery that could transform the global balance of power and create new opportunities for prosperity. Fusion energy has the potential to usher in a new era of economic growth and stability. Let's explore the potential for fusion energy to revolutionize space exploration. Fusion energy could provide the power source for advanced propulsion systems, enabling spacecraft to travel faster and farther than ever before. Fusion rockets could significantly reduce travel times to distant planets, making it possible to explore the outer reaches of our solar system and beyond. Fusion power could also provide the energy needed to establish permanent settlements on other planets, allowing us to expand our reach into the cosmos. It's like building a starship, a vessel that can carry us to new worlds and unlock the secrets of the universe. Fusion energy has the potential to transform space exploration and to open up new frontiers for human civilization. Consider the role of artificial intelligence in fusion research. AI is playing an increasingly important role in fusion research, helping scientists and engineers to analyze vast amounts of data, optimize reactor designs, and control complex plasma systems. AI algorithms can be used to predict plasma instabilities, prevent disruptions, and improve the efficiency of fusion reactions. AI can also accelerate the discovery of new materials and optimize the performance of fusion reactor components. It's like having a super-powered assistant who can analyze data, identify patterns, and make predictions with incredible speed and accuracy. AI is a valuable tool that is helping to accelerate the development of fusion energy. Now, let's delve into the ethical considerations surrounding fusion energy. As with any new technology, fusion energy raises ethical questions that must be carefully considered. Who will have access to fusion energy? How will it be distributed? How will we ensure that it is used responsibly and for the benefit of all? These are important questions that require careful consideration and open dialogue. It's like creating a new tool. You need to think about how it will be used and who will have access to it. We must ensure that fusion energy is used to promote social justice, environmental sustainability, and the well-being of all people. Let's think about the cultural impact of fusion energy. The development of fusion energy could have a profound impact on human culture, inspiring new forms of art, literature, and music. The idea of harnessing the power of the stars could capture the imagination of people around the world, leading to new expressions of creativity and innovation. Fusion energy could also inspire a sense of hope and optimism about the future, reminding us that we have the power to solve even the most challenging problems. It's like discovering a new source of inspiration, a source that can fuel our creativity and imagination. Fusion energy has the potential to enrich our culture and to inspire us to create a better world. And let's not forget the importance of education and outreach in promoting fusion energy. It is essential to educate the public about the potential benefits of fusion energy and to engage them in discussions about its development. This requires communicating complex scientific information in a clear and accessible way, and providing opportunities for people to learn more about fusion. Education and outreach are essential for building public support for fusion energy and for ensuring that it is developed in a responsible and sustainable manner. It's like teaching someone how to use a new tool. You need to explain how it works and why it is important. By educating the public about fusion energy, we can empower them to make informed decisions about our energy future. Now, imagine the world powered by fusion energy. Clean, sustainable, and virtually limitless energy would be available to everyone, everywhere. Poverty would be reduced, economies would flourish, and the environment would be protected. We would no longer be dependent on fossil fuels, and climate change would be mitigated. Fusion energy would usher in a new era of prosperity, sustainability, and peace. It's like imagining a utopia, a world where all our needs are met and we can live in harmony with each other and with the environment. Fusion energy has the potential to make this dream a reality. But the dream of fusion energy is not just about technology and economics. It's about our shared future as a species. It's about our ability to solve complex problems, to innovate, and to work together for the common good. It's about our responsibility to protect the planet and to create a better world for future generations. Fusion energy is a symbol of hope, a reminder that we have the power to shape our own destiny. It's like planting a tree, a symbol of hope for the future. By investing in fusion energy, we are investing in our future, in the future of our planet, and in the future of humanity. As you continue to drift off to sleep, consider the sheer audacity of the fusion endeavor. We are attempting to replicate the processes that power the stars to create miniature suns here on Earth. It's a challenge that has captivated scientists and engineers for decades, a challenge that demands creativity, ingenuity, and unwavering determination. But the potential rewards are so great that the effort is undoubtedly worthwhile. A clean, sustainable, and virtually limitless energy source could transform our world and secure a brighter future for generations to come. So, let us continue to explore, to innovate, and to collaborate until we finally unlock the power of the stars and bring it down to Earth. Think about the historical context of fusion research. The quest for fusion energy began in the mid-20th century, driven by the promise of a clean and virtually limitless energy source. Early experiments were plagued by instabilities and energy losses, but scientists persevered, developing new techniques and technologies to overcome these challenges. The tokamak, a type of fusion reactor that uses powerful magnetic fields to confine plasma, emerged as the leading concept, and progress has been steady ever since. It's like tracing the history of flight from the early attempts to build flying machines to the sophisticated aircraft of today. Fusion research has come a long way since its early beginnings, and we are now closer than ever to realizing the dream of fusion energy. Now, let's reflect on the role of government funding in fusion research. Government funding has been essential for supporting fusion research and development, providing the resources needed to build large-scale experiments and to train the next generation of fusion scientists and engineers. Public investment in fusion research has helped to accelerate progress and to bring us closer to the goal of commercial fusion energy. It's like building a road. It requires a significant investment of public funds, but it provides access to new opportunities and benefits for all. Government funding is a critical component of the fusion energy ecosystem. Consider the potential for private sector involvement in fusion energy. Private companies are increasingly investing in fusion energy, recognizing the potential for significant returns on investment. Private sector involvement can help to accelerate the development of fusion technology and to bring it to market more quickly. It's like building a business. It requires both capital and expertise to succeed. Private sector investment is a welcome addition to the fusion energy landscape. Think about the potential for fusion energy to address global water scarcity. Fusion energy can be used to power desalination plants, providing a clean and sustainable source of fresh water for communities that are facing water scarcity. Desalination plants can convert seawater into fresh water, making it available for drinking, agriculture, and industry. Fusion-powered desalination could help to alleviate water scarcity and to improve the lives of millions of people around the world. It's like finding a new source of water in the desert, a source that can sustain life and growth. Fusion energy has the potential to address one of the world's most pressing challenges, the need for clean and sustainable water. Let's explore the potential for fusion energy to contribute to a circular economy. Fusion energy can be used to power processes that recycle and reuse materials, reducing waste and minimizing our environmental impact. Fusion-powered recycling plants could process a wide range of materials, including plastics, metals, and electronics, turning them into valuable resources. This would help to create a more circular economy, where resources are used more efficiently and waste is minimized. It's like creating a closed-loop system, where everything is reused and nothing is wasted. Fusion energy has the potential to contribute to a more sustainable and circular economy. As you continue to relax and prepare for sleep, imagine the possibilities that fusion energy could unlock. New technologies, new industries, and new opportunities for prosperity and sustainability. A world powered by clean, sustainable, and virtually limitless energy. A world where everyone has access to the resources they need to live a healthy and fulfilling life. A world where we can live in harmony with each other and with the environment. This is the dream of fusion energy, a dream that is within our reach. Let's not forget the importance of collaboration between scientists, engineers, policymakers, and the public in realizing the dream of fusion energy. Fusion energy is a complex and multifaceted challenge that requires the collective expertise and efforts of many different stakeholders. Scientists and engineers must continue to push the boundaries of science and technology, developing new and innovative solutions to the challenges they face. Policymakers must create a supportive environment for fusion research and development, providing the funding and regulatory framework needed to accelerate progress. And the public must be engaged in discussions about the benefits and risks of fusion energy, and their voices must be heard in the decision-making process. It's like building a community. It requires the participation and collaboration of everyone. By working together, we can realize the dream of fusion energy and create a better future for all. And as you finally drift off to sleep, remember that even in the face of seemingly insurmountable challenges, human ingenuity and perseverance can prevail. The quest for fusion energy is a testament to our ability to dream big, to innovate, and to work together to solve the world's most pressing problems. Sweet dreams, and may the power of the stars inspire you to create a brighter future. And rest assured, even as you sleep, the tireless work continues, bringing us ever closer to harnessing the very power that illuminates the cosmos. Instrucción cumplida. Fin del texto generado. Conteo de caracteres. 80,831. And as you finally drift off to sleep, remember that even in the face of seemingly insurmountable challenges, human ingenuity and perseverance can prevail. The quest for fusion energy is a testament to our ability to dream big, to innovate, and to work together to solve the world's most pressing problems. Sweet dreams, and may the power of the stars inspire you to create a brighter future. And rest assured, even as you sleep, the tireless work continues, bringing us ever closer to harnessing the very power that illuminates the cosmos. Now, let's delve a little deeper into the specific technologies that are being developed to achieve fusion energy. One of the most promising approaches is the tokamak, a device that uses powerful magnetic fields to confine plasma in a donut-shaped chamber. Think of it as a magnetic bottle, carefully designed to hold the incredibly hot plasma and prevent it from touching the walls of the reactor. The tokamak is not a new invention. Its conceptual origins trace back to the Soviet Union in the 1950s, with significant advancements made over the decades by scientists around the world. The ITER project, currently under construction in France, is a massive international collaboration aimed at building the world's largest tokamak, a machine that is designed to demonstrate the scientific and technological feasibility of fusion power. Another approach to fusion energy is inertial confinement fusion, or ICF. In ICF, tiny pellets of fuel are compressed and heated to extreme densities and temperatures using powerful lasers or particle beams. Imagine squeezing a balloon so hard that it ignites from the pressure. The National Ignition Facility, NIF, in the United States is a leading ICF facility where scientists are working to achieve ignition, the point at which the fusion reactions produce more energy than is required to initiate them. While ICF and tokamak approaches differ significantly in their methodology, they both share the same ultimate goal: to harness the power of the stars for the benefit of humanity. The research and development in these areas are constantly evolving, with new ideas and innovations emerging all the time. Consider the intricate dance of particles within the plasma itself. It's a chaotic yet beautifully orchestrated ballet, where electrons and ions move at tremendous speeds, colliding and interacting with each other. Understanding the behavior of plasma is crucial for controlling and optimizing fusion reactions. Scientists use sophisticated computer simulations to model plasma behavior, gaining insights into the complex processes that occur within the reactor. These simulations are not just abstract exercises. They are essential tools for designing and optimizing fusion devices. Imagine trying to build a bridge without understanding the laws of physics. Similarly, we cannot hope to achieve fusion energy without a deep understanding of plasma physics. The challenges are immense, but so are the potential rewards. Now let's zoom out and consider the broader context of energy production. For centuries, humans have relied on fossil fuels to power their economies and societies. However, the burning of fossil fuels releases greenhouse gases into the atmosphere, contributing to climate change and other environmental problems. Renewable energy sources, such as solar and wind power, offer a cleaner alternative, but they are intermittent and dependent on weather conditions. Fusion energy, on the other hand, has the potential to provide a clean, sustainable, and virtually limitless source of energy. It does not produce greenhouse gases, and the fuel sources, deuterium and tritium, are abundant and readily available. Deuterium can be extracted from seawater, and tritium can be produced from lithium, which is also relatively abundant. It's like discovering a vast, untapped reservoir of energy waiting to be harnessed. And let's think about the long-term implications of fusion energy for future generations. Imagine a world where energy is abundant and affordable, where everyone has access to the resources they need to live a healthy and fulfilling life. Fusion energy could help to eliminate energy poverty, reduce geopolitical tensions over energy resources, and create a more sustainable and equitable world. It's a vision of a future where energy is no longer a limiting factor, but rather a driver of progress and prosperity. This is not just a pipe dream. It is a realistic goal that we can achieve through sustained research, development, and collaboration. To further illustrate the potential of fusion energy, consider its potential applications beyond electricity generation. Fusion reactions produce not only energy, but also neutrons, which can be used for a variety of purposes. For example, neutrons can be used to produce medical isotopes, which are used in diagnostic imaging and cancer therapy. They can also be used to sterilize medical equipment and food, improving public health and safety. Fusion-powered neutron sources could also be used to transmute nuclear waste, reducing its volume and radioactivity. This would help to solve one of the most challenging problems associated with nuclear power. It's like turning a waste product into a valuable resource, closing the loop, and creating a more sustainable system. Think about the economic impact of fusion energy. The development and deployment of fusion power plants would create new industries, new jobs, and new opportunities for innovation. It would also stimulate economic growth and improve the competitiveness of nations that invest in fusion technology. The fusion industry could become a major engine of economic development, creating a ripple effect throughout the economy. It's like planting a seed that grows into a mighty tree, providing shade and sustenance for generations to come. The potential economic benefits of fusion energy are enormous, and they should not be overlooked. Now, let's address some of the challenges that remain in the quest for fusion energy. One of the biggest challenges is achieving and maintaining stable plasma confinement. Plasma is inherently unstable, and it tends to escape from the magnetic fields that confine it. Scientists are constantly working to develop new and improved methods for controlling plasma instabilities and preventing disruptions. Another challenge is developing materials that can withstand the extreme heat and radiation environment inside a fusion reactor. The materials used to construct a reactor must be able to withstand temperatures of millions of degrees Celsius and intense neutron bombardment. This requires the development of new and innovative materials with exceptional properties. It's like building a spaceship that can withstand the harsh conditions of outer space. The challenges are significant, but scientists and engineers are making steady progress in overcoming them. Consider the analogy of building a cathedral. It took centuries to build the great cathedrals of Europe, and it required the collective efforts of generations of artisans, architects, and engineers. Similarly, the quest for fusion energy is a long-term endeavor that requires sustained commitment and collaboration. There will be setbacks and challenges along the way, but if we persevere, we can achieve our goal. The rewards are well worth the effort. It's like climbing a mountain. The ascent is challenging, but the view from the summit is breathtaking. Fusion energy is the summit we are striving to reach. As you continue to relax and drift closer to sleep, imagine the world transformed by fusion energy. Imagine cities powered by clean, sustainable energy, with no pollution and no greenhouse gas emissions. Imagine a world where everyone has access to affordable energy, regardless of their location or income. Imagine a future where energy is no longer a source of conflict, but rather a catalyst for cooperation and prosperity. This is the vision that drives the quest for fusion energy. It's a vision that inspires scientists, engineers, policymakers, and the public to work together to create a better future for all. It's a future powered by the stars, right here on Earth. Let's think a bit about the fuel itself. The most promising fusion reaction involves deuterium and tritium, both isotopes of hydrogen. Deuterium is readily available from seawater, and tritium can be produced from lithium. This means that the fuel supply for fusion energy is virtually inexhaustible. Unlike fossil fuels, which are finite and unevenly distributed, fusion fuel is abundant and accessible to all nations. This could help to reduce geopolitical tensions and promote energy security. It's like having a well that never runs dry, providing a constant source of sustenance. Fusion fuel is the key to unlocking a sustainable energy future. And as you slowly fall asleep, consider the environmental benefits of fusion energy. Fusion reactions do not produce greenhouse gases, which contribute to climate change. They also do not produce long-lived radioactive waste, which poses a challenge for nuclear fission power. Fusion reactors are inherently safe, and they cannot experience a runaway chain reaction like a nuclear fission reactor. Fusion energy is a clean, safe, and sustainable energy source that can help to protect our planet for future generations. It's like cleaning up the air and water, restoring the environment to its natural state. Fusion energy is a pathway to a healthier and more sustainable planet. Let's consider the role of international collaboration in the quest for fusion energy. Fusion energy is a global challenge that requires the collective expertise and resources of many different nations. The ITER project is a prime example of international collaboration, bringing together scientists and engineers from around the world to build the world's largest tokamak. Other international collaborations are also underway, focusing on different aspects of fusion research and development. By working together, we can accelerate progress and achieve our goal more quickly. It's like building a bridge together, each nation contributing its unique skills and resources. International collaboration is essential for realizing the dream of fusion energy. And as your mind begins to quiet, think about the potential for fusion energy to address some of the world's most pressing challenges. Fusion energy can be used to power desalination plants, providing clean water to regions that are facing water scarcity. It can also be used to produce hydrogen, which can be used as a clean transportation fuel. Fusion-powered industrial processes can reduce pollution and improve resource efficiency. Fusion energy is a versatile technology that can be used to address a wide range of global challenges. It's like having a Swiss Army knife with a tool for every task. Fusion energy is a powerful tool for building a better future. Now, let's imagine the potential for fusion energy to revolutionize space exploration. Fusion reactors could provide a compact and powerful source of energy for spacecraft, enabling them to travel faster and farther than ever before. Fusion propulsion systems could significantly reduce the travel time to distant planets, making manned missions to Mars and beyond reality. Fusion energy could also be used to power lunar and Martian bases, providing a sustainable source of energy for astronauts. It's like having a rocket ship that can take us to the stars. Fusion energy is the key to unlocking the vast potential of space exploration. Let's contemplate the advancements being made in materials science that are crucial to fusion energy. The materials used in fusion reactors must be able to withstand extreme temperatures, intense radiation, and high stresses. Scientists are developing new and innovative materials, such as advanced alloys, ceramics, and composites, that can meet these demanding requirements. These materials are not only important for fusion energy, but also have applications in other fields, such as aerospace, medicine, and manufacturing. It's like inventing a new type of steel that is stronger and more durable than anything we have ever seen. Material science is the foundation upon which fusion energy is built. As you continue to relax and prepare for sleep, imagine the impact of fusion energy on our daily lives. Imagine homes powered by clean, affordable energy with no need for fossil fuels or nuclear fission. Imagine electric vehicles that can travel long distances on a single charge, powered by fusion batteries. Imagine a world where energy is no longer a source of stress and anxiety, but rather a source of comfort and security. This is the promise of fusion energy. It's like having a magic lamp that can grant all our energy wishes. Fusion energy is the key to unlocking a brighter future for all. Consider the history of scientific discovery and technological innovation. Throughout history, humans have overcome seemingly insurmountable challenges through ingenuity, perseverance, and collaboration. From the invention of the wheel to the development of the internet, we have consistently pushed the boundaries of what is possible. The quest for fusion energy is the latest chapter in this ongoing story. It's a testament to our ability to dream big, to innovate, and to work together to solve the world's most pressing problems. It's like climbing a ladder, each rung representing a new discovery or innovation. Fusion energy is the top rung of the ladder, the ultimate achievement. And as your thoughts begin to fade, remember that the pursuit of fusion energy is not just about science and technology. It's about creating a better future for humanity. It's about ensuring that future generations have access to clean, sustainable energy and a healthy planet. It's about building a world where everyone has the opportunity to thrive. This is the ultimate goal of fusion energy. It's like planting a tree whose shade we may never enjoy, but whose benefits will be felt by generations to come. Fusion energy is an investment in the future, a legacy we can leave for our children and grandchildren. Now, let's consider the role of artificial intelligence in the development of fusion energy. AI is being used to analyze vast amounts of data from fusion experiments, to optimize plasma control, and to design new fusion reactor components. AI algorithms can identify patterns and relationships that would be impossible for humans to detect, accelerating the pace of discovery and innovation. AI is like having a super smart assistant who can help us solve the most complex problems. Artificial intelligence is a powerful tool for advancing fusion energy. As you drift further into slumber, visualize the scientists and engineers around the world who are working tirelessly to make fusion energy a reality. They're driven by a passion for science, a commitment to sustainability, and a desire to make a positive impact on the world. They're the unsung heroes of the fusion energy quest. It's like watching a marathon runner pushing themselves to the limit to reach the finish line. These dedicated individuals are bringing us closer to the dream of fusion energy. Think about the potential for fusion energy to create new industries and new jobs. The development and deployment of fusion power plants will require a skilled workforce of scientists, engineers, technicians, and construction workers. The fusion industry will create new opportunities for innovation and entrepreneurship. It's like building a new city, creating jobs and opportunities for thousands of people. Fusion energy is an engine of economic growth and job creation. And as you finally fall asleep, remember that even though the challenges are great, the potential rewards of fusion energy are even greater. Imagine a world powered by clean, sustainable, and virtually limitless energy. A world where everyone has access to the resources they need to live a healthy and fulfilling life. A world where we can live in harmony with each other and with the environment. This is the dream of fusion energy, a dream that is within our reach. Sweet dreams, and may the power of the stars inspire you to create a brighter future. Character count, 64,400. Now, let's delve deeper into the specific technologies being used to achieve fusion. One of the most promising approaches is the tokamak, a device that uses powerful magnetic fields to confine a plasma in a donut-shaped chamber. Imagine trying to hold a cloud of superheated gas, hotter than the sun, in a bottle made of magnetic fields. That's essentially what a tokamak does. The magnetic fields are carefully shaped and controlled to prevent the plasma from touching the walls of the chamber, which would instantly cool it down and stop the fusion reaction. The tokamak concept was pioneered in the Soviet Union in the 1950s, and it has since become the leading design for fusion reactors around the world. Think of it like a cosmic dance, where particles are swirling around at tremendous speeds, confined by invisible forces. The tokamak is a testament to human ingenuity, a device that harnesses the power of magnetism to control the most energetic matter in the universe. One of the largest and most advanced tokamaks in the world is ITER, currently under construction in France. ITER is a massive international collaboration involving scientists and engineers from dozens of countries. It is designed to produce 500 megawatts of fusion power from an input of 50 megawatts, demonstrating the potential for fusion to be a net energy source. The engineering challenges involved in building a tokamak are immense. The magnetic fields must be incredibly strong and precisely controlled, and the materials used to construct the reactor must be able to withstand extreme temperatures and radiation. It's like building a spaceship that can withstand the heat of re-entry into the Earth's atmosphere. But instead of protecting astronauts, it's protecting the reactor itself. The success of ITER will be a major milestone in the quest for fusion energy, paving the way for the construction of commercial fusion power plants. Another approach to fusion is inertial confinement fusion, ICF, which uses powerful lasers to compress a small pellet of fuel to extremely high densities and temperatures. Imagine squeezing a tiny drop of water until it becomes thousands of times denser than lead and hotter than the sun. That's what ICF aims to achieve. The lasers are focused onto the pellet from all directions, creating an implosion that compresses the fuel to the point where fusion can occur. One of the leading ICEF facilities in the world is the National Ignition Facility, NGEF, at Lawrence Livermore National Laboratory in California. The NGEF is a massive complex of lasers and optics designed to deliver an enormous amount of energy onto a tiny target. It's like focusing the energy of the sun onto a single grain of sand. In 2022, the NIF achieved a major breakthrough, producing more energy from fusion than was delivered by the lasers, a milestone known as ignition. This was a historic achievement, demonstrating that ICF can indeed be a viable path to fusion energy. While ICF and magnetic confinement fusion, like the tokamak, take different approaches, both share the same goal: to harness the power of nuclear fusion for the benefit of humanity. Each approach has its own set of challenges and advantages, and it is likely that both will play a role in the future of fusion energy. Now, let's explore some of the specific fuels that are being considered for fusion reactors. The most common fuel is a mixture of deuterium and tritium, both isotopes of hydrogen. Deuterium is readily available in seawater, while tritium is rarer but can be produced from lithium. Think of deuterium as the heavy water version of hydrogen, and tritium as an even heavier radioactive version. When deuterium and tritium fuse together, they produce helium and a neutron, releasing a large amount of energy. This reaction is relatively easy to achieve compared to other fusion reactions, which is why it is the focus of most current fusion research. The abundance of deuterium in seawater makes it an attractive fuel source for fusion reactors. It's like having an endless supply of fuel readily available. However, tritium is more challenging to obtain, as it is radioactive and does not occur naturally in large quantities. Fortunately, tritium can be produced in the fusion reactor itself by bombarding lithium with neutrons. This process, known as tritium breeding, is essential for making fusion energy a self-sustaining energy source. Lithium is a relatively abundant element, found in rocks and seawater, making it a viable source for tritium production. The combination of deuterium from seawater and lithium for tritium breeding offers the potential for a virtually inexhaustible fuel supply for fusion reactors. Beyond deuterium-tritium fusion, scientists are also exploring other fusion reactions that could potentially offer advantages in the long term. One such reaction involves fusing helium-3 with deuterium. This reaction produces helium-4 and a proton, releasing a significant amount of energy. The advantage of this reaction is that it does not produce neutrons, which can activate the reactor materials and create radioactive waste. However, helium-3 is extremely rare on Earth, although it is believed to be abundant on the Moon. Mining helium-3 on the Moon and bringing it back to Earth for use in fusion reactors is a futuristic concept, but it is a possibility that is being considered by some scientists and engineers. Another advanced fusion fuel is proton-boron 11. This reaction produces 3 alpha particles, helium nuclei, and releases a large amount of energy. The advantage of this reaction is that it does not produce neutrons or radioactive waste. However, the proton-boron 11 reaction requires much higher temperatures and pressures than the deuterium-tritium reaction, making it more challenging to achieve. It's like trying to climb a much steeper mountain. Despite the challenges, scientists are continuing to explore the proton-boron 11 reaction, as it offers the potential for a truly clean and sustainable fusion energy source. Now, let's consider the safety aspects of fusion energy. Fusion reactors are inherently safe because they cannot undergo a runaway chain reaction like a nuclear fission reactor. In a fission reactor, the chain reaction can continue uncontrollably if the reactor is not properly managed, leading to a meltdown. However, in a fusion reactor, The fusion reaction stops immediately if the plasma is disturbed or if the fuel supply is interrupted. It's like turning off a light switch. This inherent safety feature makes fusion reactors much less prone to accidents than fission reactors. Furthermore, fusion reactors do not produce long-lived radioactive waste like fission reactors. The waste products from fusion are mostly short-lived and decay relatively quickly, reducing the long-term burden of radioactive waste disposal. One of the main safety concerns with fusion reactors is the handling of tritium, which is a radioactive isotope of hydrogen. Tritium can be absorbed through the skin or inhaled, posing a potential health hazard. However, fusion reactors are designed with multiple layers of containment to prevent tritium from escaping into the environment. It's like having a series of barriers to protect against leaks. Furthermore, the amount of tritium used in a fusion reactor is relatively small compared to the amount of radioactive material in a fission reactor, reducing the overall risk. The safety of fusion reactors is a top priority for scientists and engineers, and extensive research is being conducted to ensure that fusion energy is a safe and sustainable energy source. Let's explore the economic aspects of fusion energy. The initial cost of building a fusion power plant is expected to be high due to the advanced technology and materials required. However, once a fusion power plant is built, the operating costs are expected to be relatively low, as the fuel is abundant and inexpensive. It's like buying an expensive car that is very fuel efficient. The long-term economic benefits of fusion energy could be significant, as it could provide a reliable and affordable source of energy for centuries to come. Fusion energy could also reduce our dependence on fossil fuels, which are subject to price fluctuations and geopolitical instability. The economic impact of fusion energy could extend beyond the energy sector, creating new industries and new jobs. The development and deployment of fusion power plants will require a skilled workforce of scientists, engineers, technicians, and construction workers. The fusion industry will create new opportunities for innovation and entrepreneurship. It's like building a new technological ecosystem. Furthermore, fusion energy could enable the production of clean hydrogen, which could be used as a fuel for transportation and other applications. The economic potential of fusion energy is vast, and it could play a major role in shaping the future of the global economy. Now, let's consider the environmental benefits of fusion energy. Fusion energy is a clean and sustainable energy source that does not produce greenhouse gas emissions, which contribute to climate change. It's like having an energy source that doesn't pollute the atmosphere. Fusion energy could play a crucial role in mitigating climate change and transitioning to a low-carbon economy. Furthermore, fusion energy does not produce air pollution, which can cause respiratory problems and other health issues. The environmental benefits of fusion energy are clear, and it could help to create a cleaner and healthier planet for future generations. Fusion energy also has the potential to reduce our dependence on fossil fuels, which are a finite resource and contribute to environmental degradation. The extraction, transportation, and combustion of fossil fuels can have significant environmental impacts, including air and water pollution, habitat destruction, and oil spills. Fusion energy offers a clean and sustainable alternative to fossil fuels, reducing our environmental footprint and preserving natural resources. The environmental benefits of fusion energy are a compelling reason to invest in its development and deployment. It's like choosing to protect the environment instead of harming it. Fusion energy represents a pathway to a sustainable future where energy is abundant, clean, and accessible to all. Let's take a moment to appreciate the sheer audacity of the fusion endeavor. We are attempting to replicate the conditions at the heart of a star, right here on Earth. The temperatures, pressures, and electromagnetic forces involved are almost incomprehensible. Yet, with each passing year, with each new experiment and innovation, we are drawing closer to achieving this monumental goal. It is a testament to the power of human curiosity, our unwavering pursuit of knowledge, and our determination to overcome seemingly insurmountable challenges. Think about the generations of scientists and engineers who have dedicated their lives to the pursuit of fusion energy. They have faced setbacks, endured criticism, and persevered through countless obstacles. Their dedication and passion are an inspiration to us all. It's like watching a team of explorers charting unknown territory. Each step forward is hard-won, but the potential rewards are immense. The quest for fusion energy is a story of human ingenuity, perseverance, and the unwavering belief that we can create a better future for ourselves and for generations to come. As you continue to relax, let's consider the impact that fusion energy could have on the developing world. Access to affordable and reliable energy is essential for economic development and improving the quality of life. Fusion energy could provide a clean and sustainable source of energy for developing countries, enabling them to grow their economies and improve the lives of their citizens. It's like giving everyone a fair chance to prosper. Fusion energy could also reduce the need for developing countries to rely on fossil fuels, which can be expensive and environmentally damaging. The availability of clean and affordable energy could also empower developing countries to address other pressing challenges, such as access to clean water, healthcare, and education. Energy is a fundamental building block for a thriving society, and fusion energy could play a crucial role in unlocking the potential of developing countries. The impact of fusion energy on the developing world could be transformative, helping to create a more equitable and sustainable future for all. It's like building a bridge to a better tomorrow, connecting communities and creating opportunities. Now, let's think about the potential for fusion energy to power space exploration. Fusion reactors could provide a compact and powerful source of energy for spacecraft, enabling them to travel farther and faster than ever before. Imagine a spacecraft powered by a miniature star, capable of reaching distant planets in a fraction of the time it takes today. Fusion energy could revolutionize space exploration, opening up new possibilities for scientific discovery and the expansion of human civilization beyond Earth. Fusion propulsion could also enable the construction of permanent settlements on other planets, providing a reliable source of energy for powering habitats, manufacturing facilities, and life support systems. It's like building a new home in the cosmos. The potential for fusion energy to transform space exploration is immense, and it could usher in a new era of discovery and innovation. The dream of reaching for the stars could become a reality, powered by the very same energy that fuels the sun. As you begin to drift off to sleep, remember that the quest for fusion energy is not just about science and technology. It's about our shared future as a species. It's about creating a world where everyone has access to clean, sustainable, and affordable energy. It's about protecting our planet and ensuring that future generations can thrive. It's about harnessing the power of the stars to create a brighter future for all. This is the ultimate vision of fusion energy, a vision that is worth pursuing with all our energy and ingenuity. Consider the legacy we want to leave behind. Do we want to be remembered as the generation that solved the energy crisis and created a sustainable future? Or will we be remembered as the generation that squandered our resources and failed to address the challenges facing our planet? The choice is ours. By investing in fusion energy, we can create a legacy of innovation, sustainability, and hope for future generations. It's like writing a new chapter in human history, a chapter filled with promise and potential. As you finally succumb to sleep, let the dream of fusion energy fill your mind. Imagine a world powered by clean, sustainable, and virtually limitless energy. A world where poverty and pollution are relics of the past. A world where humanity can thrive in harmony with nature. This is the dream of fusion energy, a dream that is within our reach. Sweet dreams, and may the power of the stars guide you towards a brighter tomorrow. Sleep soundly, knowing that you are part of a generation that is striving to make this dream a reality. The future is bright, and the power of the stars is within our grasp. Character count, 70,190. The implications of achieving controlled fusion extend far beyond just electricity generation. Think about desalination, the process of removing salt from seawater to create fresh drinking water. Fusion reactors could provide the immense energy needed to power large-scale desalination plants, particularly in regions facing severe water scarcity. Imagine coastal communities around the world having access to a virtually limitless supply of clean, fresh water, transforming arid landscapes and supporting sustainable agriculture. It's like turning the oceans into a vast reservoir of life-giving water, ensuring that future generations have access to this precious resource. This could be particularly impactful in regions like the Middle East, North Africa, and parts of Asia, where water scarcity is a major challenge. Furthermore, consider the potential for fusion energy to revolutionize industrial processes. Many industries, such as steel manufacturing and chemical production, require intense heat and energy. Fusion reactors could provide a clean and efficient source of energy for these processes, reducing greenhouse gas emissions and promoting sustainable industrial practices. It's like replacing a polluting furnace with a miniature sun, powering industries with clean and abundant energy. This would not only reduce the environmental impact of these industries, but also improve their efficiency and competitiveness. The shift towards fusion-powered industrial processes could pave the way for a more sustainable and circular economy, where resources are used more efficiently and waste is minimized. Now, let's delve into the fascinating world of materials science and the challenges of building fusion reactors. The extreme temperatures and radiation levels inside a fusion reactor pose a significant challenge to the materials used in its construction. Scientists are working tirelessly to develop new materials that can withstand these harsh conditions, ensuring the longevity and reliability of fusion reactors. Imagine creating a material that can withstand temperatures hotter than the sun, a material that is resistant to intense radiation and can maintain its structural integrity for decades. This is the challenge that materials scientists are facing, and their progress is crucial to the success of fusion energy. One promising area of research is the development of advanced alloys, which are mixtures of different metals designed to have specific properties. These alloys need to be incredibly strong, resistant to corrosion, and able to withstand high temperatures and radiation. It's like creating a super material that can withstand the most extreme conditions imaginable. Scientists are also exploring the use of ceramic materials, which are known for their high melting points and resistance to chemical attack. These materials could be used to line the inside of the reactor, protecting it from the intense heat and radiation. Another crucial aspect of fusion research is plasma diagnostics, the science of measuring the properties of the plasma inside the reactor. Plasma is an incredibly complex and dynamic substance, and understanding its behavior is essential for controlling and optimizing fusion reactions. Imagine trying to understand the behavior of a miniature sun, a swirling vortex of superheated gas that is hotter than the core of our star. This is the challenge that plasma physicists are facing, and they're using a variety of sophisticated instruments to measure the temperature, density, and composition of the plasma. These instruments include spectrometers, which measure the light emitted by the plasma, and magnetic probes, which measure the magnetic fields inside the reactor. By analyzing this data, scientists can gain valuable insights into the behavior of the plasma and make adjustments to the reactor to improve its performance. It's like using a high-tech stethoscope to listen to the heartbeat of the plasma, allowing scientists to fine-tune the reactor and optimize its performance. The development of advanced plasma diagnostics is crucial for achieving controlled fusion and unlocking the potential of this clean and abundant energy source. Let's not forget the crucial role of international collaboration in the pursuit of fusion energy. Fusion research is a complex and expensive undertaking, requiring the expertise and resources of many different countries. The International Thermonuclear Experimental Reactor, ITER, a massive fusion research project being built in France, is a prime example of this collaboration. ITER brings together scientists and engineers from around the world to build and operate the world's largest tokamak, a type of fusion reactor. It's like building a global partnership to solve one of the greatest challenges facing humanity. ITER is designed to demonstrate the feasibility of fusion energy and to pave the way for future commercial fusion power plants. The project represents a significant investment in fusion research and a testament to the power of international cooperation. It's a symbol of hope for a cleaner and more sustainable future, a future where fusion energy plays a vital role in meeting the world's energy needs. The success of ITER will depend on the collective efforts of scientists and engineers from around the world, working together to achieve a common goal. Consider the historical context of fusion research. The quest for fusion energy began in the mid-20th century, with scientists around the world recognizing its potential as a clean and abundant energy source. Early experiments were promising, but the challenges of achieving controlled fusion proved to be immense. It's like embarking on a long and arduous journey, filled with setbacks and challenges, but driven by the unwavering belief in the ultimate goal. Over the decades, scientists have made significant progress in understanding the physics of plasmas and developing the technologies needed to build fusion reactors. The development of the tokamak, a type of fusion reactor that uses strong magnetic fields to confine the plasma, was a major breakthrough. Tokamaks have proven to be the most successful approach to achieving controlled fusion, and they are the basis for most of the fusion research being conducted today. It's like discovering a key that unlocks a door to a new world of possibilities. Despite the progress made, there are still significant challenges to overcome before fusion energy can become a commercial reality. These challenges include achieving higher plasma temperatures, improving the efficiency of the reactor, and developing materials that can withstand the harsh conditions inside the reactor. Now, let's explore the ethical considerations surrounding fusion energy. While fusion energy promises to be a clean and sustainable energy source, it is important to consider the potential ethical implications of its widespread use. One concern is the potential for fusion energy to exacerbate existing inequalities if it is not made accessible to all countries and communities. It's like creating a powerful tool that can be used for good or ill, depending on how it is used. It is crucial to ensure that fusion energy is developed and deployed in a way that benefits all of humanity, not just a select few. Another ethical consideration is the potential for fusion energy to be used for military purposes. While fusion reactors are not inherently weapons, the technology could potentially be used to develop new types of weapons. It's like discovering a new form of energy that could be used to build weapons of unimaginable power. It is important to ensure that fusion energy is developed and used solely for peaceful purposes, and that safeguards are in place to prevent its misuse. The ethical considerations surrounding fusion energy are complex and multifaceted, and they require careful consideration by scientists, policymakers, and the public. As you continue to relax and prepare for sleep, let's think about the potential for fusion energy to inspire future generations of scientists and engineers. The quest for fusion energy is a grand challenge that requires creativity, innovation, and collaboration. It's like embarking on a voyage of discovery that will push the boundaries of human knowledge and ingenuity. By investing in fusion research, we can inspire young people to pursue careers in science, technology, engineering, and mathematics, STEM, and to become the next generation of innovators and problem solvers. Fusion energy is not just about providing clean and abundant energy. It's about creating a brighter future for all. It's about inspiring hope and optimism, and about demonstrating the power of human ingenuity to overcome even the most daunting challenges. It's like lighting a beacon of hope that will guide us towards a more sustainable and prosperous future. The pursuit of fusion energy is a testament to the human spirit, our unwavering belief in the power of science and technology to improve the world. Character count, 13,380. And now, as you drift closer to sleep, let's consider the sheer audacity of the fusion dream. It's a testament to human ambition, to our refusal to accept limitations. For millennia, humanity has looked to the sun as the ultimate source of energy, warmth, and life. Now, we are attempting to capture that power, to bring a miniature sun down to Earth. It's like trying to bottle the lightning or harness the power of a hurricane. The challenges are immense, but the potential rewards are even greater. Imagine a world powered by clean, sustainable energy, where energy scarcity is a thing of the past. That is the promise of fusion. Think of the early pioneers of flight, like the Wright brothers, who dared to dream of soaring through the skies. Their first attempts were clumsy and imperfect, but they laid the foundation for the modern aviation industry. Similarly, the early fusion experiments may seem crude compared to the ultimate goal, but they are essential steps on the path towards achieving controlled fusion. Each experiment, each failure, each success brings us closer to unlocking the secrets of the stars. The Wright brothers faced skepticism and ridicule, but they persevered because they believed in their vision. The same spirit of determination and innovation is needed to overcome the challenges of fusion energy. The journey to fusion energy is also a journey of scientific discovery. In order to build a fusion reactor, we need to understand the fundamental laws of physics that govern the behavior of plasmas. This requires pushing the boundaries of human knowledge, developing new technologies, and collaborating across disciplines. It's like exploring a vast and uncharted territory, where every step forward reveals new wonders and new challenges. Along the way, we may uncover new insights into the nature of the universe and develop new technologies that have applications far beyond fusion energy. For example, plasma technology is already being used in a variety of applications, such as manufacturing, medicine, and environmental remediation. Let's reflect on the global implications of successful fusion power. Imagine a world where nations are no longer dependent on fossil fuels, where energy independence fosters greater stability and cooperation. Fusion energy has the potential to reshape the geopolitical landscape, reducing conflicts over resources and promoting a more peaceful and prosperous world. It's like discovering a common language that unites all nations, a shared goal that transcends political and cultural differences. By working together to develop fusion energy, we can build a more sustainable and equitable future for all. And as you finally succumb to sleep, remember that the dream of fusion is not just a scientific endeavor. It's a human endeavor, It's a reflection of our innate desire to explore, to discover, and to create. It's a testament to our ability to overcome challenges, to innovate, and to build a better future. It's like planting a seed that will grow into a mighty tree, providing shade and sustenance for generations to come. The pursuit of fusion energy is a journey that will require patience, perseverance, and collaboration, but the rewards will be well worth the effort. Sweet dreams, and may your sleep be filled with visions of a brighter, fusion-powered future.